Okay, sorry about that. So I will very briefly introduce what we do in world weather attribution, which is sort of what Sarah has already introduced a little bit at the beginning. It's the same method that has been used in the first papers. So I will not go very much into the methods, but talk a little bit about the kind of results that we get and the kind of statements that would be the end of, sort of the overarching end result of a rapid study. So we asked the question, how has climate change altered the likelihood and intensity of an event of this type to occur? So the first thing that is important to highlight here is that we have to define the extreme event, and at least the quantitative answer that will come out of this attribution study is valid only for this very specific event definition. And what you can see here on the left-hand side, so you see so this is sort of for an extreme heat wave in Madagascar, a study that we have done last year, where we looked at 3 different aspects of the heat wave. So we looked at the maximum temperature over 7 days in Antananarivo, where the capital. We looked at the minimum temperatures over 7 days in Antananarivo, and we also looked at the whole of October over Madagascar. So average mean temperatures over all of Madagascar. And so for all these, and the quantitative results for all these event definitions are slightly different, whereas qualitatively they all come out with a very, very similar result, which is not surprising. So, and in all cases, in all attribution studies that we do with the world weather attribution approach, we first look at the observed data and either look at it as, just as you can see on the left-hand side, just creating probability distributions of how would this event look like, how would all possible events that are following the event definition, so all possible Octobers, look like if all the data that we have observed would happen in today's climate, so at 1.2 degrees of global warming that we already have. And then we ask the same question again: how would possible Octobers or possible 7-day nighttime temperatures in Antananarivo look in the world that would have been if it was 1.2 degrees cooler? And so this is the difference between the blue curves and the red curves. On the left-hand side, just as a standard probability distribution, so it's not a standard, it's a GEV, but it's as a probability distribution, and in the middle you can see it as a return time plot. So you can see when you look here for the observed event, which is the pink line, you can see that is about, in today's climate, it's about a 1 in 20 year event. But when you look at the blue curve here, you will find that this event, in exactly the way that has been observed, would be basically impossible to occur without human-induced warming. That doesn't mean there would not have been a heat wave, but it means that a heat wave defined in exactly this way and of this magnitude would not have occurred without human-induced climate change. And we've summarized, and this is sort of the summary of this finding that you can see on the right-hand side in this graphic. So on the first, on the top row, you can see before or without human-induced climate change, you see none of these pink points in the sort of possible events, possible October temperatures over Madagascar, whether in today's climate with 1.2 degree of warming. It is something that you would, and this is for the whole of October. Before I just showed the nighttime temperatures where it was a 20-year event, but for the whole of October, it's in today's climate about a 1 in 100-year event. So once in any given year, you have a 1% chance of such an event to occur. And but it would become, in a 2-degree world, it would be a much more frequent event happening every 5 to 10 years. But we can, of course, use the same methods to ask the question: how has the magnitude of the event changed? And this is what you see at the bottom here, where in the middle you have the event as observed. That was about 25 degrees average October temperatures over Madagascar. And without climate change, and that today is a 1 in 100-year event, and so the 1 in 100-year event, October temperature would only have been about 23.5 degrees in a world without climate change. And then you can also see how that changes with the future. And so this is the kind of results that we get for heat extremes, where the quantification of the event very, very, very sensitively depends on how exactly we define the event. So that means in the quantitative, so whether this event has been made 1,000,000 times more likely or 100 times more likely, is very strongly dependent on how exactly we look at the event. So whether we define it as the October or the 3-day maximum or the 5-day maximum. But the fact that climate change played a huge role and made this event much, much more likely, we are absolutely certain about that. So we have very high confidence in this part of the results. And so this is, and on the left-hand side, you see sort of the kind of statements that we would formulate from this in our main findings. And these are other examples that you can find on our website, where for heat waves, we always find that climate change played a big role. And sometimes it is that the actual observed magnitudes would not be possible without climate change. But we can, of course, do the same kind of approach for rainfall events. And there you have just also from last year, some of the studies, and I just circled one here. Sometimes when we don't have, and Sarah has pointed that out, sometimes actually defining the event is not really possible because we don't have data that really characterizes what has actually led to the impacts. And sometimes we also find that climate change does not play a big role. And just two more before my 5 minutes are up, just two more examples to show this. So this is for a heavy rainfall event in the Black Sea that led to quite a lot of flooding particularly around Ukraine late last year. And here you see in this graph with lots of blue and red bars, these are the results from the detection in blue. So the change in likelihood from different observed products and from different models. And you can see that the observations show an increase in the likelihood of the rainfall on average, but not all of them. But all the models show an increase in the likelihood of such 3-day maximum precipitation to occur. And so in this case, we have concluded that climate change made this event about a factor of 2 more likely. If we would have just looked at the statistical approach that you can see here, that would maybe have been an overconfident statement. But of course, we have also more lines of evidence that we use. And in this case, it's very much our physical understanding, which is called the Clausius-Clapeyron relationship, so that we know from that relationship that a warmer atmosphere can hold more water vapor. And that will come out, especially as high heavy rainfall, sort of on the time scale of hours to up to 3 to 5 days. And so because of that, we think we have more confidence in this result than we would have if we didn't have this reasoning. And we also looked at the wind speeds in this area, where we found that in the models, in the observations, there's a small decrease in wind speed. And in the models, they are all over the place. And in this case, we don't really have also any theory that would support to trust models or observations more or less. So in this case, we can just conclude that there is no evidence that climate change altered the likelihood and intensity of this 3-day wind speed event. So that was just a very brief run through to some of the types of results that we get with this probabilistic method, where we always answer the question, how would an event of this type, as defined in the event definition, how has that changed because of human-induced climate change?